So let me start here. So I want to start in the following way. I was once on the tenure and promotions committee of NYU. So this is at the college level, not the department level. And we had a physicist who was up for promotion. And we were reading through the letters, and I paraphrasing what the letter sounded like, but I came across a letter that sounded like this. It said, if this theorist's work is supported by experiments that are planned to be run in the coming months, his work would have a considerable and major accomplishment. And that struck me at the time because statements like this are much more likely to occur in a science like physics than in economics. For example, Einstein in the 1920s said, if the observations of the red shift in the spectra of massive stars don't come out quantitatively in accordance with the principles of general relativity, then my theory will be dust, okay, and ashes. Now that's a statement that I defy anybody to tell me they've ever heard coming from an economic theorist, okay? So nobody in my department, and I've hung around in the proximity of theorists for a long time, nobody has run up to me in the hall and said, Andy, I just finished a great theory paper, and I hope that when it's finished, and when you're finished testing it, it'll prove to be correct. Okay, that I've never heard happen. What they do come up to me and say is, Andy, I have finished a great theory paper. Isn't it beautiful and elegant? Okay, so theory papers are judged on their elegance, but they're not judged, and there's not a requirement necessarily that they be tested and that the proof of their usefulness is in the testing, okay? So in short, the relationship between theory and experimentation in economics has either been non-existent or perhaps strained for a long time. Okay. Now, so it appears also that economics there isn't the same requirement that the theories we have be tested, okay? And I'm always amazed when you look at the NASA science program in the United States that the missiles they launch actually make it to the moon and come back. I mean, they're amazingly successful. And the reason that that occurs is because every component of what goes into the missile has been tested, okay? So they test the propulsion system, the theory of orbits, the theory of gravity, the heat shields. All of that stuff has been tested. Therefore, it's not perhaps so miraculous that the missile actually launches and goes to the moon. Now, in economics, we build models without really testing their components, okay? So I remember years ago, I was at a conference, and there were two economists sitting at the bar, and they hadn't seen each other for a while, and they said to each other, you know, we should write a paper together. Why that follows, I don't know, just because they're having a drink, but they said, we should write a paper together. And they started to talk. I don't know if it was on this topic, but this could have been their conversation. So they said, well, what should we build a model on? So, well, why don't we build a model about the way binary random markets work? What I mean by that is markets where people meet randomly in a binary fashion. One is a buyer, one is a seller. They have to decide whether they should trade. Very much like the experiment that Chamberlain did years ago and the kind of stuff that's in the textbook by Bergstrom and Miller, okay? But in any case, people meet randomly and they have to decide whether they should form a contract. So one economist might say, well, what are the components that we need for this model? Well, they say, well, we have to learn, since people are going to be meeting each other, we have to have some theory of search. So how will people search for these prices? So, well, one of them might say, well, maybe if the environment is stationary, we can just have them use a reservation price. Okay? So that might be the way that they search. That's the search component. But when they have, once they meet, then we need a theory of how they're going to form prices. So what should we do? Maybe we'll use the Nash bargaining theory, or maybe we'll use another theory that's called the sealed bid mechanism of Chatterjee and Samuelson, which is a theory of price formation in auctions with incomplete information. That's okay. That makes some sense. And when will we know if a price is accepted? Well, maybe it'll be accepted if the current offer is better than the continuation value of continuing in the game. And so you can build a model that way. The only aspect of building a model that way is that you realize that none of those components that went into that model have ever really been tested. So now you have a model that has 5, 6 components. None of them are tested. So the punchline of what I've just said is that probably if economists built rockets, I don't think they would necessarily make it to the moon because none of the components in their theories are necessarily tested. Now, so why is economic theory developed with no connection to experimental validation? Well, there's lots of reasons for that. Perhaps it's that economic theory grew out of a body of philosophy that did not have an empirical tradition. Or maybe it was when economics was formalized, and let's attribute that to Samuelson for the moment. And he famously said, economics isn't an experimental science. People didn't think that you could do economics that way. That might make sense. But whatever it is, economics seems to have grown up without a tradition of putting theories to at least experimental tests, and not tests, other types of tests either, perhaps. Okay, so what is the relationship between economic theory, and by this I mean NF, conventional theory, and experimental economics? Well, I think it's true that everybody believes that economics is the queen of the social sciences, the most rigorous social science. And it's mostly because of the rigor and the precision that economists use in their thinking, which I think is, of course, very good. So consider the following statement. When the price of a good increases, demand falls. So that's a statement. Okay? Now, you ask somebody on the street if that's true, they'll say clearly it's true. If you raise the price of something, the quantity demanded is going to fall. But as economists, we know that that statement is not 100% correct, because there are things in the world called Giffen goods, and there's a relationship between the income effect and the substitution effect. And that could affect the law of demand. So economic theory helps us to understand that what statements are correct and aren't correct logically, okay? So economic theory is a search for those circumstances that must exist in order for a statement about behavior to be logically correct, okay? And a theorist is somebody who provides the if statements that are necessary for the completion of all if-then logical statements. So another way of putting it, which is hidden down on the bottom, is that economic theory is really an anti-bullshit device, okay? It protects us from loose statements being made. And there's a very interesting book by a philosopher called Harry Frankfurt called On Bullshit, which is a very small book which is an interesting thing to read. But the interesting thing about economic theory is that it disciplines our thinking. It tells us when things follow, A follows from B, follows from C, or the other way around, actually. Okay, but by this definition, economic theory has no connection to the real world, okay? It provides a description of what the world would have to look like in order for statements to be correct, okay? But by that definition, theory must be wrong by construction, because there's no a priori reason why finding out what the world must look like in order for a statement to be logically correct has any relationship to what the real world is like outside. This is just a logical statement. In other words, the world may not look like the world hypothesized by the theory. It's just that the world would have to look that way if this statement is going to be correct. So all theory, therefore, is wrong until validated, okay? Now, as you'll see, I'm not going to make any claims that economic theory isn't useful. It's extremely useful, but you'll see the reason I say that. So how can a science based on a wrong theory function? Why should theory be used to guide experiments? And the point here is what I call strong and wrong theory. In a paper that I wrote in 2007, I argue that economic theory may be wrong by construction, but it is also strong by definition in that its assumptions are transparent, and as a result, its predictions can be evaluated logically, okay? So it's strong in the sense that it allows economists to make point and interval predictions that other social sciences can't do, okay? So take the ultimatum game. Go to any social science other than economics and ask them what's going to happen in the ultimatum game if you have to split $100, or the dictator game, and the answer is it depends. But not us, okay? We know exactly what's going to happen. I'm going to offer you a cent, and you're going to accept. So we make predictions, okay? That's not a problem for us. It's just that it turns out that those predictions aren't correct, okay? But I'm not claiming that that's bad, okay, as you'll see in a second. So the value of economic theory is that it makes predictions that are likely to be wrong, which furnish us with testable hypotheses, and the behavior may deviate from the predictions in ways that are likely to be informative and systematic and likely to lead to better and new theory, okay? So theory is valuable because it structures our search for the truth, not because we expect its predictions to be correct. So I wouldn't wring my hands because, oh, economic theory predicted that and it's wrong, you know, ha, ha, ha. That's not the point. The point is that it structures our investigation for what the true behavior would look like. What we hope for by doing experiments is that if the theory fails, it fails in ways that are revealing and interesting, that lead us to be able to do something with it, okay? So we may learn as much from a theory that's a failure as one that's a success, okay, or more. Now, actually, Bill Clinton said a similar thing in politics, says when people feel uncertain, they'd rather have somebody that's strong and wrong than somebody who's weak and right. And I know Herb's going to talk about the US election, but I don't think Bill Clinton meant that somebody can be as wrong as Donald Trump is and still be somebody that we should look for. But I'll stop right there.
He didn't say that's good.
Yeah, he said that's understandable. That you would, if somebody's offering you a strong leadership, you take them up, even if what he's saying isn't right. In any case, I know that my talk would stop here if I went down this street, so let me continue. No, I told you that my talk could stop here if I started this, so I don't want to do that. Okay, so examples of how strong and wrong theory can be useful, well, we know many of them. Take the ultimatum game. So you have the ultimatum game. If you posit selfishness, subgame perfection, it leads to a prediction, but the prediction turns out to be wrong. But that led to other theories that would help explain that phenomenon, okay? Take expected utility theory. Expected utility theory leads to predictions, leads to contradictions via Allais and others. So that leads to non-expected utility and prospect theory, okay? Take Nash. Nash makes point predictions in many games. In experiments, these predictions are many times not met. However, it led to new theories like quantum response theory, if you consider that, or refinements of Nash equilibrium that help us. So what I'm calling a strong and wrong theory actually can be very useful because it actually gives us a platform for which to study deviations from it, which are very useful. Now, you might argue, I'm not arguing this, but you might argue that behavioral theory does not exist except as a reaction to conventional theory. So prospect theory was a response to expected utility. Quantum response was a response to Nash. Cursed equilibrium is a response to conventional auction theory. I'm not saying one needs conventional theory as a platform, but it's actually a very useful way to seek what you consider to be reasonable or predict or accurate behavior in the real world. Now, where does economic theory get into trouble? And here I'll cite my advisor, who many years ago told me the following story, which I think is really great. He said that Niels Bohr, okay, a famous physicist, was once in an argument with his colleagues, and he was really getting steamed about what they were talking about. And he finally got so angry that he had to leave the room, and when he left the room, he said, "You guys are not making sense, you're only being logical," okay? And that, I think, really sums up a lot of what goes on with economic theory, because we're great at being logical, we're just not always great about making sense. And there's lots of examples here. For example, take the 100 times round finitely repeated prisoner's dilemma game. We know that that game says that you should defect in every single round. That's, by the logic, is completely correct. That's logically correct, okay? It just doesn't make sense, because you know that people aren't going to do that. For a variety of reasons, they're going to experiment in the beginning of the 100-round PD game. Another example, which I don't have here, is the idea that we shouldn't vote, okay, because nobody's going to be pivotal in the thing. That's logically correct, but people vote for a large variety of reasons. It really doesn't make sense. If you were to explain to somebody, "Now, don't go to the polls this year," it's unlikely that you'll be pivotal. I suspect they'll still go to the poles, okay? And there's, of course, the Centipede game, which is a game where you either take or pass. I'm not going to explain it, but the more you pass, the more the joint payoff will be better than the beginning one, but there's always a temptation to take on the way. Here again, the theory predicts logically that we should take on the first round, but we know from experiments of McKelvey and Palfrey that only 6% of the time does the game end going down on the first take, okay? Now, so that's really a difference between being logically correct but just making no sense, okay? People don't do that, and there's good reasons why they might not. Okay. Yeah, and I'll just mention one other thing, which is that when you go to test theory in the lab, it's not enough to demonstrate that the results that you get are consistent with the theory, but you also have to verify that they're consistent with the theory for the reasons stated by the theory, okay? Because there are many times that you can get behavior that's consistent with a Nash equilibrium, but because people are using heuristics or something like that. And the way to verify that is to do some comparative statics, okay? And there's a nice paper by Gorey and Holt called 10 Treasures, where they have one paper where they expect the theory to work, but then they set up other parameters for this game, so they vary it, and they demonstrate that while it worked in the treasure treatment, which is the one they expected it to work, when you change the parameters, it doesn't work anymore. One of the explanations for that could be that it wasn't Nash behavior that was driving the original confirmation, but some other heuristic, and then when you change the parameters, that heuristic failed to work on the change setting, okay? Okay, so what have I said? Well, I said that the most efficient way to discover empirically valid behavior perhaps is to use a theory as a benchmark, as a platform, or a straw man, if you wish, upon which to judge deviations from its predictions in an attempt to sort out what assumptions are violated, okay? So I think it's wrong to look at economic theory for valid predictions. I would just rather look at it for logically consistent and intelligible views that make predictions that can be tested. And then it's the deviations from the theory, if there are any, which become the interesting objects. We should be as happy to find interesting deviations as confirmations. And what's nice is to find out the reason why I've said this, why they fail, okay? Let me just say one last thing. So one of the questions you could ask is what type of theory is the most useful, okay? And in economics, you know, it's funny about economics. We don't really study methodology in economics. The only thing that we have is this one thing written by Milton Friedman in 1950, or 53, whenever it was. And everybody harks back to that as the justification for why they're doing what they're doing. But Friedman, in that original paper, suggested that what we want from a theory is that it be a good predictive theory, that it makes predictions of what behavior should be. So he has this quote that says, "The ultimate goal of positive science is the development of theory or a hypothesis that yields a valid and meaningful, i.e. not truistic, predictions about phenomena not yet observed. Predictions need not be forecasts of future events. They may be about phenomena that have occurred, but observations on which have yet to be made or are not known to the person making the prediction." So Friedman seems to be putting predictive theory, or the aspects of theory that are about predictions, to be above explanatory theories, okay? So explanatory theories are theories that explain phenomena ex post given the data, okay? So for an explanatory theory, you have to have you have the data, and then the question is, how do you hook up a theory that explains the phenomenon? Now, Friedman would put this at a lower level than predictive theory. However, there are many theories that we have that are very useful that are explanatory theories. So for example, if you take level K theory, that's probably a classic case of explanatory theory, because what you have to do with level K theory is the way the ball gets started is you have to define what the level 0 behavior is going to be like. And then everybody best responds after that. However, people are given the data, so many times they choose the level K type as the one that will be useful for describing the distributions of the other types over the data. So really, if your objective in level K theory is to predict what the distribution of cognitive types are in the population, you can't get the ball rolling there unless you have the data and then you fit that to what you have there. So, but that doesn't mean that level K theory isn't useful. It just means that it's more of an explanatory theory than a predictive theory. Of course, you can make it predictive by trying to predict out of sample and things like that, but basically that's not the game there. Quantum response theory is also, to some extent, an explanatory theory, because what you try to do there is you try to match behavior, you try to match the theory to the data, and the way you do that is by choosing one parameter, which is lambda, which is the precision parameter, and the exercise there is to find what the value of that parameter is. However, this theory does make comparative static predictions, which don't rely on the data. So it's a kind of a mixture in some sense. Okay. I think I've said this, summarizing what I've done, and I actually have more time to get to the other stuff. So let me get to the other stuff. So let me talk about this. So I want to tie in what I'm going to say about something that I've written to the theme that I've just been talking about, or in some way, or at least I'm going to try to do that. So here's the question. So if originally one of the rationales for experimental economics, as discussed by Vernon Smith and Charles Plott, was that experiments in economics were to be done for two reasons. One was to test economic theory, and the other one was to test the properties of economic institutions or mechanisms. So it was tightly connected with this mechanism design literature, okay? And it was also there to test, in the beginning, of course, the theory of markets, but other theories as well. Those were the two original justifications given by them for doing that. But then this raises, so if you want to test economic theory, one question that's raised when you do an experiment is, in what environment should I test this theory? And there are two conflicting or two environments where there's some tension between them. Should I try to test the theory in the environment that was written down by the theorist, okay, which is one, and when you design experiments you have to worry about this, or should I test this mechanism in the environment in which it's used in the real world, okay, which may be different than the environment that the theorist wrote down, but really we care about how mechanisms function in the real world, so testing it in that environment is an important thing as well. So there's a tension there. So I want to look at that tension between the environments in which you can test theory by looking at the school matching problem that I've worked on. Okay, so the theory of school matching, which is the theory of how do you allocate students to schools. So you have a set of students, you have a set of schools. What you need to do is match the schools, the students with the schools. Okay, so that each student is in one school. Okay. In theory, typically, this is a theory of a static one-shot game played non-competitively. That's the way this is typically modeled. It's usually not dynamic. It's a one-shot game played non-cooperatively. And what is that game? Well, the game is all the students submit orderings, their preference orderings over the schools. And given the mechanism that's used, the mechanism matches the students with the schools. So the game that's played between the students is what ordering over the schools should they submit, okay, to the mechanism designer. But that's not the way that this problem is played in the real world. In real world settings, it's not a one-shot static game. And there's two ways in which it deviates from that. One is that when it's your kid's turn to go to school, say your child is in the 5th grade, you go to the playground and you meet other parents, and once you put your kid on the slide, you feverishly talk about what your strategy should be in submitting your preferences about the school matching thing. You know, should you put your third choice first because, you know, everybody's going to try to get your first choice, and there's all this strategic stuff. They also talk about how good the schools are, but let's just talk about the strategic aspect. So there's advice that's given between parents at any given point in time. We'll call that horizontal advice, and that's something that affects the way people make decisions, okay? And I've written a paper with Ting Ting Ding on that. But there's another way in which it differs, which is that parents who've been in the match before, okay, and have finished and gotten a school for their child, give advice to the current generation of parents. And then those parents give advice to the next generation of parents, and that goes on. So there's this intergenerational advice that gets done. One generation gives advice to the next, which gives advice to the next. And you can call that vertical advice, if you'd like, okay? Now, yeah, the problem with, and I'm only going to talk about this kind of intergenerational advice, the problem with what happens here is that if over time the advice that gets passed down from generations to generations, the wisdom that people have accrued from this process, is not connected to the theory in any way, the results of this mechanism can get out of the control of the mechanism designer. People can be giving advice where in some sense the best advice should be state your truthful preferences. It could be that they're passing down advice which is not that at all, and people are following it, and behavior can get very far away from what the mechanism designer had planned for the static one-shot game. Okay? So let's take a look at that. Here's a school choice problem. What is a school choice problem? By the way, this is going to be very cryptic because I thought I'd only have 7 minutes left, and I actually have 25. But in any case, but that might allow me to talk about a second paper. Okay, so a school choice model with I students in N schools consists of a triple, P, Q, and pi. So P is the preferences of the students over the schools. So these are just ordinal rankings, okay? Q are the school capacities. So it just says how many seats are in each school. And pi are the school priorities, which is just a set of rules that dictate how students are allocated to a school when more students apply to that school than they have seats for, okay? And it just says if kid A and B apply to that school, but one of them lives within walking distance of the school, he gets to go into the school and the other one doesn't, okay? So it's just a set of rules. And this would be this would be a vector of the set of students that have priority in that school, okay? Now, as a result, this is a one-sided matching problem because the schools don't submit their preferences over students. It's only the students that submit preferences over schools, and the schools are required to behave according to these priorities. They don't issue preferences over the students. Okay, so the outcome of a student is a student assignment. So it's a matching from the set of students to schools, where this indicates the school assignment. And then all the normal definitions apply. So a matching is Pareto efficient if there's no way to improve the allocation of a student without making another student worse off. Note that it's only the students' welfare that we care about here, not the schools. They're just mechanical things. A matching is efficient if it maximizes the surplus generated for students. This is important. The matching is stable if there is no student-school pair, okay, such that student I prefers school S to her assignment under the matching, and there is another student J with lower priority than student I assigned to school S under that matching. So this means that that student should be able to kick that other one out because he has a higher priority, okay? And a mechanism is strategy proof if truth-telling is a dominant strategy for all students, okay? So these are the criteria that they'd like to impose on mechanisms. And there's a famous result that says, there's no mechanism in this matching world that can satisfy all three criteria. So you can't get efficiency, stability, and truthfulness in a mechanism, but you can have mechanisms that do 2 out of 3. Okay? Now, I'm going to look at 2 mechanisms. One is the Gale-Shapley mechanism, and I'm not going to describe how it works, but I'll just say that the Gale-Shapley mechanism is strategy proof. So it's a weakly dominant strategy for this mechanism for you to submit your truthful preferences. So it's very simple. You just go, you tell the truth about, I like school 1 better than 2, better than 3, and you walk away. And it does not guarantee efficient results, but it does do one thing, is that it guarantees, if preferences are strict, it guarantees a stable outcome. And not only that, but in this setting here, it guarantees that stable outcome which is student by student best compared to all other stable outcomes. So it gives the students the best stable outcome that they can get, and they all unanimously agree on that. Another mechanism that I'm going to look at but not really talk about is the Boston mechanism. This mechanism has no properties, okay? The only point about that mechanism is that it's one that is still used and was used historically in many schools. So many times in these papers, they compare all of the mechanisms they look at to the Boston mechanism. Okay. I'm not going to explain the design, but I'll explain enough about it. So you have groups of 5 subjects. They have preferences over 3 objects, which could be schools, okay? And there are 5 units of the school. So for example, there's school object A, B, and C. There are 2 units of A, 2 units of B, and 1 unit of C. So there are 5 objects, okay, or 5 seats in schools, and 5 students, and we have to match them in that way. The students submit their ordinal rankings over the school mechanisms to the administrator, and the administrator uses the mechanisms to define the matching. And to cardinalize the preferences, what we do is we give people, if you get your first choice, you get 24. If you get your second choice, you get 16, and if you get your third choice, you get $4. So that's the ranking that you have. That's why you like one school more than the other. It's incomplete information. You're not told the preferences of the other subjects, but that you do know that they have these 3 numbers attached to them. You just don't know what they're attached to. Okay? Yeah. Okay. So what experiment did we do? Well, we did the following experiment. One experiment, which we call the repeated experiment, people come in groups of 5, and they play this game 20 times. Every round they keep their type, okay, which means they keep their preferences and priorities, but they're matched with different people of other types. So there's always the same configuration of types over the 20 rounds. But the important point is that people come here and they play the game 20 times, okay? That's contrasted to what we call the intergenerational treatment, which we think is closer to the way the world works, unless you have 20 children, in which case the first model is correct, okay? But that's typically not the case. So what happens in the real world is that you have one child, and subjects are organized into generations and play the matching game once. So 5 people come in, they're given their preferences, they're given their priorities, they state a ranking, they get their payoff, and then what they do is they tell the person in the next generation of their type, they give them advice. And what's the advice? The advice is a ranking over the schools and the text. They can write whatever they want in the text. They say, you should do this because, okay? So they do that. And their payoffs are the following. The payoff of any subject is the payoff in their lifetime, what they get when they're in the match, plus 1/2 of what their successor earns that they give advice to. So this gives them incentive to give good advice to the next generation. Okay? So this game is then played in an intergenerational way for 20 rounds, or for 20 generations, and we're going to compare the behavior of the 20 generations to the repeated behavior of the 20 rounds, and we're going to see if they differ. Okay? And if they do, and in what way they differ. Okay, I don't know if the next slide is the only result I'm going to present, and I don't know if it's there because I don't want to break their, no, okay, good. Well, this is the design. Now the tension drum rolls. No, that's not it. Okay. So what are the questions we're going to ask? Well, we're going to ask, How will behavior evolve over the 20 generations? Okay. Will a convention of behavior get established and get passed down from generation to generation? And will this convention converge to something? Okay. If it converges to something, will it converge to the static equilibrium? Okay. And will behavior differ between the generational treatment and the repeated treatment? So that's what we're interested in finding out. And these are the results. This is what I'm interested in. This is the Gale-Shapley mechanism. This is periods 1 through 5, 6 through 10, 11 through 15, and 16 through 20, every 5 rounds, okay? And this is the fraction of people who tell the truth. Now, in this mechanism, remember that truth-telling is a dominant strategy, weakly dominant, but a dominant strategy, okay? And the blue line is the fraction of people who report truthfully over time, and you see that it starts off at about 62% and goes up to about 77, 78%. So in the repeated treatment, they kind of get it. They kind of move towards full truthful revelation. But in the intergenerational treatment, this thing monotonically decreases, such that in the last 5 rounds, only 44% of people are telling the truth. Now, this is what I said about the beginning, that this is a case where you see that the mechanism is just getting away from the control of the mechanism designer. He doesn't want this to happen, okay? But why is it happening? Because people are giving this advice. So how do you explain this? There's no much difference here. I'm not going to talk about that. But how do you explain this difference? Well, the difference turns out to be a difference between the type of learning that takes place in the repeated treatment and the type of learning that takes place in the intergenerational treatment. In the repeated treatment, boy, I'm skipping slides here. Okay, good. So in the repeated treatment, what type of learning might you think is going on here? Well, it's kind of like experiential reinforcement learning. Why? Because the following might occur in this experiment. I come into the room and I read the instructions. After I read the instructions, I say to myself, okay, I have 6 strategies here, 6 different preferences I can submit. Which one do I like better? So I get attracted to these strategies. Okay, so there's an initial vector of attractions over the strategies. And then I choose one of them, and I submit that preference. And then I get a payoff. And based on that payoff, I reinforce that strategy or not. Okay? So I rearrange my attractions. And if I use a strategy and it does well for me, I'm more likely to use that again because it becomes more and more attractive. So over time,
When they read the instructions, do they have any sense that this could be, that truth-telling could be the optimal?
We don't tell them that. We could make a statement. A lot of.
One way you could do it is to have them answer questions.
Oh, I see. To let us know whether they have an inkling over that. Yeah. So there you go. I could have done that. Okay. But I didn't. But that would have been interesting. Although you can tell something by the fraction of people who submit truthfully in the first 5 rounds, at least. Okay, so that says something. Okay. Yeah. Now, one interesting thing about this is that there's a theorem that says if you play a game that has a dominant strategy, that's a strictly dominant strategy, but here it's weakly, but let's just do it anyway. If you have a game that has a dominant strategy, and you and everybody else are using reinforcement learning to learn what to do in that game, then then as time goes on, you're going to converge to the dominant strategy, which is truthful revelation here. Okay? So that means that we should expect in the repeated treatment, if people are learning by reinforcement learning, that over time they should be converging to telling the truth in that game, which is kind of what we observe here. Now, if we left this go to 100 periods, who knows where that might go, okay? So what happens in the intergenerational treatment? That's a different type of learning. That's really social learning. Okay? So what happens in that experiment? I come into the lab, I read the instructions. After I read the instructions, I have to choose my strategy. The only information that I have, in addition to my attractions of reading the instructions is I get a piece of advice from the previous generation. And then I have to choose. And after I choose, I leave, and the next person comes in, and they play the game once, and with my advice. Okay? So in every generation, you have a bunch of naive decision makers coming in, making their decisions on the basis of only one piece of advice. Okay? So this type of learning is very different than reinforcement learning when you can play the thing very often. And as a result, in this paper, we structurally estimate this and we do simulations, and we kind of demonstrate that this kind of social learning model is different. Ernst?
Do they give the wrong advice then?
So you can see, so what's interesting in the advice, as I said, I thought I had 7 minutes. But what you can see in the advice is that there are these sequences of periods. There's these where one guy gives a piece of advice that's not truth-telling, and he says, look, a big thing that to do instead of truth-telling is put your second choice first. That's safe, they think, okay? Even though they shouldn't, okay? But it looks safe, okay? So they say, put this choice first, and then they use some phrase like, it'll be better for you if you put your second choice first. And then that phrase gets carried over from generation to generation, okay? Everybody's telling the next generation something that sounds like that until it gets broken by somebody. The chain gets broken.
They've adopted this advising strategy in which they tell the other person exactly what they would have done if they had a chance to replay this game.
Right.
Then you would have gotten the same dynamic as with the reinforcement, no?
No, because first of all, they may not be listened to. Yeah, I'm glad that that's what you would do. I mean, all you're telling me is what you would do, but I'm a different person, I think, and so it's plus with the reinforcement learning, I've chosen something 15 times and it's always worked out for me, and now I choose it a 16th time and it's a bad payment, but I know that 15 times before that it was good, so I persist in it. But if I just come in and use it once and it's bad, then I tell the next generation it's bad, you see? So you don't get this accumulated experience in this thing. Okay, so, but the punchline of what I'm trying to say here is that sometimes you have to decide in what environment you want to test theory, okay? And now this is not particularly relevant for theory, this is more relevant for mechanism design. And what's important in testing mechanisms is to test it in an environment where it's used in the real world rather than...
Theorists hate this argument. So I would imagine that you get this paper reviewed and you get a theorist who you have a hard time.
Well, I mean, so what's new in the world? I mean, this...
It's the wrong incentive.
Yeah. Actually, we're doing okay with this at the moment, You have to...
Well, they say this is not what the theory says. And so refuting the theory doesn't make sense here. So they are not governed in their assessment by the external validity.
But it is what the theory says in the environment that we tested in. So in other words, you could write down a theory of intergenerational advice where you get some kind of self-confirming equilibrium that leads people to behave that way. So, I mean, I think they might, if they were smart, they might like it, because it tells you that it's not enough to just test the theory in the environment that the theorist has written down. What happens when you take that to the real world? Things may differ. So I can't prescribe what theorists like. But luckily, we have a revise and resubmit, and so who knows? Okay? Yeah. Okay, let me just say one last thing. I used to have 10 minutes, but now I think I have 6 or something like that. 6, okay, good. So here's a 6-minute version of this. So this is something that I'm thinking about now, and the point is kind of the same, just to try to tie it back to the methodological thing. Here we also have a problem about thinking about how to look at games, behavior in games, which is more consistent with the way people play them in the real world than the way that the theory writes them down, okay? So here's the point. When studying or teaching game theory, one common assumption is that people play or concentrate on one game at a time. So if you're ever teaching game theory, you put up the prisoner's dilemma, and you talk about dominant strategies, okay? And you act as if that's the only game that this decision maker is thinking about, and all your concentration is on that. However, we know that in the real world, we play many games simultaneously and make many decisions simultaneously. So our big problem is how do we split our attention across the games that we have in front of us to play, okay? And then based on the amount of attention we allocate to a game, we have to decide how we're going to behave. So it's really a two-step thing. How much attention do I pay to thinking about the game? And conditional on that, how do I behave? So what do we do in this experiment? This is attention in games with Ala Avoyan and myself. This is Sanjit's student from Georgia, where he taught sometimes. So his influence is everywhere. What happens in this experiment? Well, people come in and they have two games that they see. There'll be numbers in these matrices, but I'm just putting them up like that. And they're told that we're not interested in having them play this game. They're given 10 seconds. We're not interested in having them play this game. What we're interested in is telling them that at the end of the experiment, they're going to have X seconds to play this game. We're not telling them what X is, but they're going to have X seconds to play this game. And we want them to tell us in 10 seconds what fraction of that X seconds they want to allocate to thinking about game A, or game 1, or game 2. So their choice now is not to play the game. It's to decide how much time or how much attention they want to pay to game 1 or game 2. Okay? So that's what their task is. And what are we interested in? Well, we're interested in those 10 seconds, what features of the problems or games they faced will attract their attention. So when they look at these numbers, they'll have to make a quick judgment. I think this game is more important for me to pay attention to than that game. Okay? And does the manner in which a player plays a given game depend on the other games that he's simultaneously facing? So this is a point that I think might be perhaps interesting. You see somebody playing a game. He's acting like a complete moron. Your conclusion, the guy's a moron. However, given the fact that he's splitting his attention across several games, it very well may be that he's doing the best he can given the attentional constraint that he has generally. So one of the punchlines here is that we have to look at games in a kind of more general equilibrium context rather than as in a kind of partial equilibrium context that we have. I have 3 minutes? 4? Oh, well, okay. Here's a bunch of games that we had people look at. We had many more, but this is a particular set we'll call the comparison set. So these are the kind of games that people look at, okay? So they might be given this game and this game to look at for 10 seconds. And then we ask them, split up your time. What fraction of the time do you want on game 1 and what fraction on game 2? Okay? And that's how it goes. Now, what do I have here? So what I want to demonstrate here is that how much time you allocate to a given game, which is this game up here, is going to depend on what other game you were forced to divide your time between when we showed you the screen. And here are the other games that you could have faced when you also were shown that game. So do you get what I'm trying to say here? Here we have the average amount of time you allocated to this game, but when you were allocating time to this game, you were either facing this game, this game, this game, or et cetera. Okay? So if we take a look at this graph, what does this graph say? Well, it says that when the other game that this person faced was this game, which is called chance, doesn't really matter right now, they allocated a lot of time to this one up here. But when they were playing this game, which is the Battle of the Sexes 100 game, they allocated much less, and even much less here. So the amount of time they allocate to this game depends on the other game that they were actually had to choose between. Now, the question is, in the last 2 minutes, does the amount of time that you allocate to a game, or the amount of, quote, attention you're paying to that game affect your behavior? Because if it didn't, we wouldn't care. But the question is, does it? And we have this diagram here. So, oh boy. So what we have here is whether or not you paid less than the mean amount of time to playing this game, which you can't really read here, or more than half. So we split the population into 2 parts, those that allocated less than the mean and that allocated more than the mean. It could be the median, but we happen to use the mean here. And then here, we looked at how much time they allocated to this game. Okay? So for people, in this game it's, oh, I can't really see what that is, but it's a game. Trust me, it's a game. For that game, people who didn't concentrate on it very much chose strategy A this percent of the time. But those who concentrated a lot on it switched. I think this is a prisoner's dilemma game. So people who paid little attention initially played cooperatively. People who eventually spent more time played non-cooperatively. This is another game. This might be a coordination game or something like that. You see the same result. Now this is a nice game. This is just a coordination game with 800, 800, 500, and 500 here. People should be focused on that. And you see that this is 100%. So 100% of the time they chose strategy A, no matter how much time they allocated to it. Okay? And that's because it seemed to be pretty obvious to them that that's what they should do, no matter how much time they allocate to that game. Okay, I'm going to finish. So what's my conclusion? So I'm actually quite positive about conventional economic theory. I think it's an indispensable part of behavioral and economics. Its main benefit, however, is not giving us predictions necessarily. Well, it gives us predictions, but the main benefit is helping us structure the search for proper behavioral models, and it should not be judged on whether its predictions are correct. I mean, theorists, of course, want them to be correct, but that's not what anything I would think about. Confirmation is wonderful, but interesting deviations are also exciting. And finally, when testing theory, we need to do so both in an environment envisioned by the theorist, but also in the environment in which the theory is used in the real world. So that's my spiel.